Good morning, students. The continuation of size dependent properties only we are going to see in this lecture video. Here, the molecules, nanoparticle, the various size of the molecule, nanoparticle, and bulk properties, bulk particles are given. So, how it is distinguished with help of the atoms? We are going to see this. Example, molecules. Here you can see this. Molecules means up to 1 to 10 atoms will be available. That atoms are combined atoms are called, they will call as the molecules. Then the nanoparticle means up to 10 power 2 to beyond the above 10 also, sometimes 13 above 10 13 to up to 10 power of 6, they will call as the nanoparticles. The atoms are consist combined atoms are they will call as the nanoparticles. Then above 10 power 6, that is microscope, after micrometer, they will call as the bulk particles. They will call as the bulk particles. These things are very approximate number only, but sometimes they will take as say about 10 power 6, beyond that they will take as say nanoparticles, but in 10 they will call as the 10 number 10 atom combination of 10 atoms, they will call as the nanoparticles. Next, size. Here in this slide we explain the size. The number of nanoparticles exhibits unique properties due to their high surface area to volume ratio. That is we already saw that. Here you can see this. They are spherical particle has a diameter of 100 nanometer, so the volume is nothing but we are getting that 5.24 into 10 power minus 22. Similarly, the surface area is nothing but 3.14 into 10 power minus 14 meter cube. So what is that volume? This gives the approximate surface area to volume ratio is greater than the 10 power 7. That is greater than the 10 power 7 only. So it means 10 is 10 power 7 is to 1, which is significantly larger than the macro sized particle. So in the macro sized particle, it has nearly 1 atom only. They will taken as a is to 1. So that means it is greater, which is significantly larger surface area to volume ratio. As the surface area to volume ratio increases, so does the percentage of atom at the surface area, and surface forces become more dominant. So that is a very important point we already saw in the previous class itself. Generally accepted material properties are derived from the bulk, where the percentage of atoms are very minute level only. These properties changes in the this is the important property changed in the nanoscale. Okay, here the size is given. Nanoparticles diameter is 1. The nanoparticle diameter is like that. They will give surface area to volume ratio is how it is varying. When the nanoparticle size is increasing, the surface area to volume ratio is decreasing. Here the graphs clearly indicating how the nanoparticle diameter increases, the surface volume ratio is decreasing. So the ratio increases dramatically when the nanoparticle diameter drops below the 100 nanometer. Here, with help of the gold, they will with help of gold and silver, they will clearly given how the size is varying. With the help of the size, how the color will be varying. Everything clearly given. Here you can see this. The AG nanoprism is nearly to the 100 nanometer, it will be given as a red color. Then gold spheres 100 nanometer, it will be here yellow color. Similarly, for 50 nanometers of gold, AU spheres given as a green color. So when it is AG 120 nanometers, approximately only they will given. It is nearly to the light white, or you can take as a brown, light brown. Then the silver age is okay, up to 80 nanometer, it gives as a light blue. Then it will be for thick blue for 40 nanometers. Okay, yeah, as percentage of atom at the surface increases, the mechanical, optical, electrical, chemical and magnetic properties will be varying. Okay, here similarly the melting point as a function of the particle size, we already saw that, but here with help of the graph they clearly explaining. Here you can see this at nanoparticle sizes, diameter sizes will be increasing. Okay, what will happen? You can see this, the melting temperature will be increasing. Okay, when it is decreasing, the melting temperature also decreasing. Here melting point is a shape. particles may center together at lower than, okay, centered together will be lower than the expected temperature. Rods can melt and form spherical droplets if heated too high. We already saw in the naturally we already see saw sorry already saw that thin films can form pinholes. Continued heating can lead to de-wetting behavior and island formation. Crystal structure. Most solids are crystalline with their atoms are arranged in regular manner. The arrangement of the atom impacts the functionality of the material. That is the important, very very important point, because all the atom arrangement will give the proper structure of the crystalline. So some solids have their order presented over long range of crystal. Amorphous materials, like example glass and wax, lack long range order, but they have but they can have a limited short range defined as a local environment that each atom experience. Okay, this is the very important important point, why amorphous materials are having less strength also. This is the not having, even though not having the proper structure. This point will be clearly explained to you. Then crystal structure. The spatial arrangement of atom in a crystal lattice is described by a unit cell. The very thing here you can see this, the lattice, how the lattice will be defined with help of the unit cell. The unit cell is the smallest possible volume that can display a full symmetry of the crystal. Many materials have preferred unit cells. Here you can see this, the preferred unit cell, how it will be there, everything at all. In a 3-dimension, a unit cells are defined by 3 lattices. Here you can see this A, B, C is with help of the 3 lattices they will be explaining. This leads 4 to 14 Brevis lattice. Okay, each having characteristic on the lattice constants, angles, centering of atom in the unit cell. With help of these things we can develop 14 Brevis lattices. Sorry. Here you can see this. For cubic unit cell there are 3 centering types are given. Here you can see this simple cubics. Each corners are having the atoms. Here you can see the bodies, they will call as the body center cubics. Okay, here all the corners are having atom, also in the center of the body having one atom. In face center cubic all the corners are having the atom, and each face center is having one atom. So crystal size and crystal structure continues in this slide also. Most metals in the solid form of closed packed lattice, close packed lattice, then Ag, Al, copper, cobalt, Pb, then Pet and Rh are the face center. They will example for the face center cubic. Similarly, external close packed examples are Mg, Nd, Os, Re and Ru, Y and Zn are the examples. Similarly, body center cubic examples are chromium, lithium, selenium are the simple examples are body center cubic, and also SCP depending upon the formation of energy. Next, structural magic number. Nanoparticles have structural magic number, that is optimum number of atoms that leads to a stable configuration while maintaining a specific structure. That is the important 2 mark question for you. Okay, then structural magic number is equal to the minimum volume and maximum density configuration. If the crystal structure is known, then the number of atoms per particle can be easily calculated. Here you can see this magic number cluster. Cluster is combination of the number of atom. Okay, combined atoms. Okay, here number of cells are 1. Then number of cells are 2, then number of cells. So with the help of the number of cells, the number of atoms in the cluster is 13. Then number of cells in the cluster is 55, then 147, then 309, then 6. So the percentage of surface atoms are 92, 76, 63, and 52. So magic number is equal to the, sorry, I'm going to continue this slide. The magic number is nothing but equal to the cluster as a complete and a regular outer geometry. Okay, here the one relation is giving for how to find the number of atoms in a cell. Y equal to 10 n square plus 2. When I am going to substitute 1, I am going to get the number of atoms in the cluster. How in the cluster? So maximum number of nearest neighbors is they will consider metal to example in the metal to metal HCP packing, decreasing the percentage of surface atom as a cluster sizes will be increasing, or the number of atom will be increasing. Okay, next here size and crystal size structure is defining. For n layers, the number of atom n is an approximately spherical FCC structure. Okay, FCC. Then the nanoparticle is n is given 1 by 3, 10 n cube minus 15 n square plus 11 n minus 3. Similarly, the number of atom on this surface of the n surface is 10 n square minus 20 n plus 12. Okay, based on this we can easily find out the number of surfaces available in the atom, number of atoms. Similarly, the size and the crystal structures are okay. They will given this photo is explaining how number of FCC nanoparticle atoms are available. Then I am going to consider say cell number 1, diameter is 1d, then total is 1. This on the surface. Okay, it will be 100% of the surface only. Similarly, up to 100 cell numbers, diameter is 199d. Similarly, the surface percentage is 3 only. They were calculated and given in the slide. Then Wolf crystal shape. This used to determine the shape of the crystal when formed under the thermodynamic equilibrium condition. Okay, under the thermodynamic equilibrium condition, surfaces are equal to the areas of high energy. Different facets, the various phases are available in the crystals. So different phases have different surface energies. Okay, then objective to minimize the total surface energy in the x facet. Here they will given the wolf crystal shape. Here the plots represent the simplified view of the crystal faces in 2 dimensions, that is x and y dimension. Here x is infinity and y is equal to 1. So x is equal to x, that means 0. They will consider as 0, and y equal to 1. The distance is 1 because it will be given as a distance, but in the x direction it will be infinitive. So family of crystal faces is included in the all of the following phases: 1, 0, minus 1, 0, 0, 1, and 0, minus 1. Here you can see this. You can explain like that. Then Miller indices in 2 dimension. Where the plane is crosses x and y. Here you can see this 1, 1, it will be crossing. Similarly 1, 1 here, 1, minus 1, 1, minus 1, minus 1, minus 1, and 1, minus 1. Like that you can give the family of the crystal structure. Here you can see this. These points are explaining 1, 0, 1, 0, minus 1, 0, and 0, 1, and 0, minus 1. Similarly, Wolf crystal shapes are defining. You can define with help of this things. Here, draw outline innermost faces are to determine the shape of the crystal. The result is that high energy phases exposes less surface area to the external environment. Here you can see this. This outer surface is having the lower surface area. Here we are having the high surface area.